Okay, we will continue our discussion of drops and drop size distributions in space, and we will begin with a few questions and try to answer them.
When we were dealing with drop size distributions, we came across a spatial drop size distribution and a temporal drop size distribution. What is the primary difference between the two drop size distributions?
Okay. The question relates to different measurement techniques of measuring drop size distributions in space. We discussed spatial sampling and temporal sampling. We want to see if we can maybe use an illustrative example to differentiate between the two but it will be a simplistic illustrative example, but sufficient to understand the complexities involved. Okay, let us take a couple of monodisperse droplet generators. So, these are monodisperse generators. I will number them 1 and 2. The whole idea of monodisperse means that they are producing drops of one size. Okay, let us say these drop the generator 1, and we will just call this example problem number 1 for now. Let us say droplet from generator 1 is 100 micrometers. So, essentially it is producing a stream of droplets that are all diameter d1, moving with some velocity v1, and they are produced at some, let us say we will give these some numbers, let us say 1 meter per second, and the number rate of production is, let us say, 10 per second. So, we are producing 10 drops of 100 micron diameter per second, and each one is being ejected out from the needle at a speed of 1 meter per second in the axial direction. Want you to note that the number frequency is nothing to do with velocity, they are completely different measures of how fast the drop may be moving. Likewise, we will say D2 is much smaller, let us say it is only 10 micrometers. We will start by looking at the situation where V2 and N2 are the same. We will see what this generator would give us in the for a spray. So, essentially my atomizer is composed of two little needles, one producing 100 micron drops and another producing 10 micron drops. If I take a region of interest that includes the tip of this nozzle, let us say something that is 1 meter in diameter, and the width really does not matter. This is my imaging interrogation area or imaging area. So, that is the area that my camera is capturing. So, a simple way could be that I have a backlight and the backlight is illuminating the drops, and when I view from the front I see the shadow of the drops. So, the individual shadows form circles in a snapshot in a frozen picture, and from those individual circles I can get the size of each droplet. Okay. Since I am producing, so let us see if each droplet is moving at 1 meter per second and the spacing between droplets is 1/10 of a second. So, the production spacing between droplets is 1/10 of a second, and so if I take one snapshot that is 1 meter in height, let us say the time spacing between drops is 1/10 seconds. This is coming from the fact that n1, I will call this n1 dot, that is number production rate. Okay. So, if I take n1 and n2 both are 10 per second, which means I am producing drops, one drop every 1/10 of a second, which is the same as saying the time spacing between the drops is 1/10 of a second. Since the velocity of the drop is 1 meter per second, if the interrogation area has a height of 1 meter, the drop is going to be resident in there for 1 second. Okay. So, the second thing is to do with the residence time. It's 1 second. Which means I am going to, if I take a snapshot, I am going to have ten of diameter d1 and 10 of diameter d2. Okay. So, if I now look at in any given snapshot, I want to calculate, let us say, the simple arithmetic mean diameter, which is sum over all the drops di divided by n. Okay. If I do this, I have 10 times 100 micrometers plus 10 drops of 10 micrometers divided by 20, which happens to give me a number like 55 micrometers. This is the diameter I get. I will put this ds for spatial sampling. For the same situation, if I do temporal sampling, so this is spatial sampling mean diameter equal to 55 micrometers. For the same spray, if I do a temporal sampling, what do I get? So, the whole idea of temporal sampling is that I am going to remain at some cross section here, let us say, okay. This is my sampling position, and I am going to accrue statistics of drops passing through this point. I will call this cross section AA. Okay. I am going to measure. So, the next thing we will talk about is temporal sampling. The steps involved are measure the diameter, passing through AA over a fixed, this is very important, period of time. Okay. So, what happens if I do this? Now, I know that I am producing 10 drops per second, which means if I sample for 1 second, I will do it just to move away from 1. If I sample for 2 seconds, I would have sampled 20 100 micron drops and 20 10 micron drops. So, again I can calculate the temporal mean diameter. So, as it turns out, the temporal mean diameter is also 55 microns. Now, we have two parameters characterizing two separate measures of a time associated with the drop. One is the velocity, another is the frequency of production. So, we will keep the same frequency of production and see what happens if we change the velocity. Okay, that is our first test. So, I will now take the exact same situation . Except I am going to make this V2. So, I will call this my example 2. Okay. Example 1 was fairly straightforward, we got the same mean diameters whether you sample in the time domain or whether you sample in the spatial domain. So, now if the drop is moving fast, and I will go back to the same exact spatial now the drops are moving fast, these drops are moving at 10 meters per second. In relation to these drops that are only moving at 1 meter per second. But the time spacing in the production is exactly the same. So, if I did a spatial sampling just like I did before, consider spatial sampling first. If the drop is moving at 10 meters per second and the length of this whole thing is 1 meter, it takes 1/10 of a second to traverse the whole meter. Okay. Whereas, I am producing one drop of 10 microns every 1/10 of a second. So, what are all the possibilities for how my right side of the image will look like? Okay, so, I want to distinguish between the right and left side, because it is like a very simple spray, it is like a two monodispersed sprays superposed, and if we understand how this works, we can get a feel for how the real spray works. So, the drops that are 10 microns in diameter are moving at 10 meters per second, that is, a given drop is in this frame for only 1/10 of a second. So, I have three possibilities for the right half, depending on how my one, depending on whether I am, when I take the snapshot, I could have one drop somewhere in the middle of the frame like that, okay, and there is the time before the next drop is produced is like further in the future compared to my frame, and the previous drop has already exited the domain. So, I could have one drop in the frame, or there is also a very remote instance, say for example, if this was not 1 meter, but 0.9 meters, okay, or slightly less than 1 meter. I could also have the instance where the drop has just exited and I have not yet produced the next drop on the right half. So, I will have no 10 micron drop. I could also have, again, if it is slightly greater than 1 meter, I could have the instance where I have one drop just about to exit and another drop just about to be produced. So, really speaking, I have this one drop in the frame, somewhere in the frame, or I could have no drop or two drops. These are all remote possibilities, and only when L is not equal to 1 meter exactly. Okay, if L equal to 1 meter, then if this is exactly mathematically correct, then it has to, I will only see one drop, the drop has to exit before I see the other drop. Okay. So, really speaking, the only possibility we want to look at seriously is this one drop of 10 microns, that is the only possibility. On the left hand side nothing has changed, I will still see 10 drops, right, because the time production of each drop is the time separation between each pair of drops is 1/10 of a second, and they are all queued up one behind the other. So, in 1 meter physical space I will have 10 drops one behind the other if they are all moving at 1 meter per second. Okay. So, essentially I could have, if I do this spatial sampling correctly, ten 100 micron drops and one 10 micron drop. So, if I do my spatial mean average, approximately 92 microns. If I do the time sampling, let us see what we find. So, temporal sampling on the same system, is based on the fact that I have one drop coming through here every 1/10 of a second, and so if I again sample for 2 seconds I will get 10 or 10 times 2 20 100 micron drops, and 10 micron drops, right. If I sample for 2 seconds, which means again if I do the so, if I look at what happens, what is it that I am measuring when I do spatial sampling, what is it that I am measuring when I do time sampling. If I time sample at for 2 seconds, that means I am getting 20 drops that are moving that are at 100 microns. Now, you have the sampling, it is like a sampling cross sectional area in which I am allowing these drops to go through. So, every time a drop goes through I have a way of getting its diameter, measuring its diameter. So, the rate at which drops can go through here in a steady spray has to exactly equal the production frequencies. Whatever be the production frequencies, that is what I end up measuring here. Okay. So, what you get in a time sampled in the time sampling in the time domain is basically related to your n1 dot and n2 dot. We can look at an example 3 where we go back to V2 being 1 meter per second and n1 dot or n2 dot being, let us say, 100 per second or 1 per second. Okay. You will see that. So, let us actually complete that example just so we gain our complete understanding of the whole problem. I want to go back to example 3 where V2 is back to being 1 meter per second, but N2 is now down to 1 per second. When you do that, you end up seeing, now I am going to erase this part here because it corresponds to the previous example. But what do I what could I possibly look for when I do spatial sampling in this? The fact that I am only producing that all the drops are moving at 1 meter per second. Okay. So, in any the drop is resident in this frame for 1 second, but I am producing only 1 drop per second. Okay. So, if I look at what I will end up observing, ಇದೇದೋ ಸ್ಟಕ್ ಆಯ್ತು. So, if we look at the rate of production of the drops of size 2 in this example 3, it is 10 times slower than the rate of production of drops of size 1. So, if I do spatial sampling, I am producing 1 drop per second and that 1 drop is going to move at 1 meter per second. That is, the drop that is produced will remain, I only have one possibility that they will only have that there will be 1 drop in the frame, the other 3 where it is just about to exit or just about to be produced are sort of rare events. So, 2 drops and no drops are both rare events. So, in the 1 meter frame that I have, the only possibility is that I will have 1 drop resident in there. It is moving at 1 meter per second and it is going to take 1 second to traverse through the frame, and it is going to be 1 second after this drop is produced that the next drop will be produced. So, whereas on that is the story for the left half for the right half. For the left half, the story is not changed. So, if I do the spatial sampling, what I have is 10 drops. Now, does the size of the domain make a difference? So, if I have instead of 1 meter, if I sampled over 2 meters, will that make a difference? Chances are, again the drops are spaced. So, the for any given drop d I, okay. So, let us say in this case I take a situation where V I divided by N I dot is, and let us say L is the sampling domain height. I will take a situation where I have L is much greater than any of V I divided by N I dot. Okay, so, let us say I will recreate this situation where V I is not 1 meter per second, but let us say 10 centimeters per second or 1 centimeter per second, and N I dot is like 1 per second or 10 per second, and we end up packing the drops much closer now. Okay. Will this, if L is very large in comparison to the max of V I dot V I divided by N I dot, what you end up seeing is that you will have these kinds of possibilities of whether I have 99 drops or 100 drops on the right hand side as opposed to 1 or 2. So, the percentage error associated with the number of drops being slightly different on one side versus the other keeps going down. So, the spatial sampling gives you a result that is closer to the production rate sampling, to the time rate sampling. Think of an extreme situation where I could sample an infinitely long domain, in which case every drop produced is at the moment present in the domain. So, if I took a snapshot of this domain, it cannot be different from having sampled every drop produced in time. So, essentially when we say spatial sampling and temporal sampling, they are different as far as finite times of sampling are concerned. It is only when I say I am sampling over 1 meter, sampling over 2 seconds, that you will get 2 separate answers. If you go to the extreme case of sampling over an infinitely long domain and an infinitely long time, those 2 answers are exactly the same. Those are true representations of the production rate. That is the SMD, or that is a mean diameter based on the production rates, is what I can completely tie to the atomizer performance. Everything else could be an artifact of the way I am sampling in the spray, right. So, essentially if I take these 2 sprays and if I have L be much greater than V I divided by N I dot, then the spatial sampling and the temporal sampling become very close to each other. And I will say that both of these would end up becoming equal to the production sampling. actually production sampling is something that is already exactly equal to the temporal sampling, but just to sort of have a physical feel for sampling in time being different from sampling at the nozzle exit. If I now look at, I can now come back and quantify this effect of this size of the domain. So, in going, let us say instead of 1 meter, if I went up to 10 meters, same exact system, what are the possibilities that I have here? Instead of 3 possibilities, I actually have many more, but we will rewrite this. If I am sampling over a 10 meter long domain, same rest of the performance characteristics are the same. I am producing 1 drop every second, and I have 10 drops of N1 dot being produced. So, essentially I have 10 drops that are 10 microns in size, and 10 drops that are 100 microns. The spacing between 1/10. So, I will have 100 drops that are 100 microns in size. The spacing between a pair of drops being the same, for the L1 is 0.1 meters, I will call this L1. So, if the size was 10 meters, I will still end up getting the proportion of the drops D1 to D2 would still remain the same, because the physical spacing between them is still the same. Okay, so, the mean drop sizes tends towards this the temporal sampling mean drop size. The spatial mean drop size tends towards the temporal drop size, as long as the sampling remains distinct, as long as the sampling domain is of a finite size. As you go to a larger and larger domain size, the two values converge to a particular unit.